All right, today we are going to dive into one of the most important foundational concepts in all of electronics. It's this tiny, invisible switch that, and I'm not exaggerating here, makes our entire digital world go round. Let's get right into it. So I want you to just think about something for a second. What's the one little component tucked away inside your phone, your computer, maybe even the lights in your room? What is this microscopic switch that's the secret engine behind, well, pretty much everything you own?
Well, the answer is the PN Junction. I know, it doesn't sound very flashy, does it? But it is truly the unsung hero of modern technology. So in this explainer, we're going to pull back the curtain and really understand how this thing works, and maybe more importantly, why it works the way it does.
And calling it the heart of electronics, that is not an overstatement. Not at all. Because if you can really get your head around how this one little thing operates, you pretty much unlock the secret to how everything else in the digital world functions. And seriously, its fingerprints are everywhere. The simple diode that acts like a traffic cop for electricity, the LEDs lighting up your screen right now, the transistors that are the literal brains of your computer, even solar cells. At their very core, they're all just clever arrangements of this PN junction.
So, how do we even build one of these things? Well, it all starts when we bring two very special materials together. Let's meet the two main characters in our story, the P-type and the N-type semiconductor. First up, we've got our P-type material. A good way to remember it is P for positive. Now, its whole deal is that it has a bunch of what physicists call holes. The best way to picture this is like a parking lot that's almost full, but it has a few empty spaces. Those empty spaces, the holes, can kind of move around as cars shift, and they act just like positive charges. And then on the other side, we have the N-type material. You guessed it, N for negative. This one's the opposite. It's a semiconductor, like silicon, that's been doped with an impurity that brings a few extra electrons to the party. These electrons aren't tied down to any one atom, so they're just free to zip around, carrying a negative charge. Now, on their own, neither of these materials is all that special. But the real magic? That happens the very instant they're joined together. Right at that interface, that border between the P-type and the N-type, a chain reaction kicks off that creates something amazing. This whole process creates this crucial feature, a natural built-in barrier. We call it the depletion zone. So let's break down exactly how it forms. And it happens, boom, almost instantly, in three main steps. First, diffusion. You've got all these free electrons crowded on the N side, so naturally they just rush across the border to fill up the empty holes on the P side. As soon as that happens, we get step 2, recombination. An electron finds a hole, settles in, and poof, they basically cancel each other out. This creates the final step, the depletion region, a zone right at the junction that's been cleared out or depleted of any free-moving charges. And that name, depletion region, makes perfect sense, right? It's been depleted, emptied out of all those free-moving electrons and holes. So now you have this weird, insulating neutral zone sandwiched right between your two conductive materials. But here's a really fascinating side effect. The atoms that gave up those electrons and holes, well, they're left behind with a charge, and they can't move. They're stuck. This creates a small but really important electric field across that depletion region. The best way to think about it is like a little speed bump or a hill that makes it harder for any more electrons to cross. We call this built-in voltage the barrier potential. And look, this isn't just some abstract theory. You can actually measure it. For silicon, which is the workhorse of pretty much all modern electronics, that natural barrier is about 0.7 volts. It's a tiny number, but it's the key to everything. Okay, so we've got this natural barrier just sitting there. The next logical question is, can we control it? Can we mess with it? And the answer is a big yes. This is where we get to actually flip the switch by applying our own voltage from the outside. So let's say we want to turn the switch on. This is what we call forward bias. We connect the positive side of a battery to the P side material and the negative side to the N side. This external voltage basically pushes against that internal barrier. It gives the electrons and holes the energy they need to get over that little hill, which makes the depletion region shrink way down, and suddenly, a whole bunch of current can flow right through. This is the on state. Okay, but what if we flip the battery around? Now we're talking about reverse bias. We connect the negative terminal to the P side and the positive to the N side.
Now, instead of fighting the barrier, our voltage is helping it out. It's pulling the electrons and holes even further away from the junction. The depletion region gets wider, that barrier gets stronger, and boom, electricity is blocked. This is our off switch.
So when you put them side by side, the difference is it's night and day. Forward bias gives you a super thin depletion region, super low resistance, and lots of current. Reverse bias, you get a wide depletion region, crazy high resistance, and pretty much zero current. It is a perfect electronic switch. You know, this whole one-way street behavior, it's so fundamental, so incredibly useful that we give this component its own special name, the diode.
And this right here, this is the big aha moment. A simple PN junction, just by its very nature of existing, is a diode. Its entire job is to be a one-way gate for electricity. That's it. I think the absolute best way to picture this is a one-way valve in a water pipe. You know the kind. Water can flow one way and push the little flap open, no problem. But if it tries to flow backward, it pushes the flap shut, and the flow is blocked. The PN junction does the exact same thing, just for electricity. This whole concept is so important that the question you see on screen is one of the all-time classic questions in technical interviews. If you can nail this answer, you've really truly understood the heart of semiconductor physics.
And you know what? Here's the beautiful, simple answer. In forward bias, you're pushing against the natural barrier, you're shrinking it, and you're letting current flow. In reverse bias, you're helping the barrier, widening it, and blocking the current. It is all about controlling the width of that depletion region. So, if you're going to take just one thing away from all of this, let it be this. The PN junction is the most basic, fundamental, controllable, one-way gate for electricity. And from that one simple idea, we can build the entire mind-bogglingly complex world of modern electronics. Just think about it. From transistors that are the size of a few atoms, all the way up to massive solar farms, it all comes back to this one simple one-way gate. Every time your computer thinks, it's just billions of these gates opening and closing. So the real question becomes, now that we know how this fundamental switch works, what's the next big thing we're going to build with it?